Hello everyone, I am Guruprasad Upadhya, H.O.D, Dept. of Mathematics, Canara Engineering College, Bantval. This is the fourth lecture in 18MAT41, Complex Analysis, Probability and Statistical Method, Module 2. So in this I am going to discuss Cauchy's Theorem and Cauchy's integral formula in complex analysis. Cauchy's Theorem. The statement, if f of z is an analytic function and f dash z is continuous at each point within and on a closed curve C, then integral over C f of z dz is 0. Proof. Let f of z is u plus iv. U is real part of the function and v is imaginary part, and dz is dx plus I dy. Then integral over C f of the dz is, just multiply these two, u into dx plus iv into I dy, that is I square v dy. I square is minus 1, therefore real part is u dx minus v dy, its integral, plus I into integral over C v into dx plus u into dy. Just separate the real and imaginary parts. Now, in second sem you studied Green's theorem in vector calculus. We have Green's theorem in plane stating that if m and n are two real valued functions having continuous first order partial derivatives in a region R, bounded by the curve C, then integral over C m into dx plus n dy is double integral over R partial derivative of n with respect to x minus partial derivative of m with respect to y dx dy. So this is Green's theorem. So we can apply this Green's theorem in the right hand side of this expression, because if f dash z is continuous, then u v partial derivatives of u v with respect to x and y are continuous, because f dash z is continuous. Therefore, partial derivatives of u and v with respect to x and with respect to y are all continuous, and you are able to apply the Green's theorem. Here in the first integral, u is nothing but m and n is minus v. Therefore, integral over C u dx minus v dy is nothing but double integral over R minus v partial derivative with respect to x minus partial derivative of u with respect to y. Here partial derivative of u with respect to x minus partial derivative of v with respect to y. So applying this theorem to the two line integrals in the right hand side of the equation 1, we get minus double integral over R dou v by dou x plus dou u by dou y dx dy plus I into double integral over R dou u by dou x minus dou v by dou y dx dy. So this is by Green's theorem. Here n is minus v, m is u. Here n is u, m is v. But given that f of z is analytic, since f of z is analytic, by Cauchy's Riemann equations, CR equations, ux equal to vy, that means dou u by dou x equal to dou v by dou y, and vx is minus uy. Take this minus uy left side. So ux plus uy is 0 and ux minus vy is 0, and hence vx plus uy is 0 and ux minus vy is 0 means the right hand side of this integral. So this is 0 and this is 0, therefore integral over C f of z dz is 0. So this is Kaushis theorem. Now I am going to discuss some corollaries in Kaushis theorem or consequence of Kaushis theorem. The first one is, if f of z is analytic in a region R and if P and Q are any 2 points in it, that means P and Q are the 2 points in the region R, then integral of f of z dz from P to Q is independent of the path joining P and Q. So this concept is I already discussed in the third lecture, but here using Cauchy's theorem I am going to prove this concept. Now this is the region R, take any 2 points in this region. Let C1 and C2 be 2 paths joining P and Q. From P to Q there are 2 paths, one is C1 and one is C2. From P to Q, C1 and C2. Now consider the closed curve, that is from P to Q along C1 and from Q to P along C2 in opposite direction. So it becomes total closed curve. Since f of z is analytic in the whole region and hence it is analytic in within and on the closed curve C, and hence integral over C f of z dz is 0 by Cauchy's theorem. Now C is split into 2 parts. One is from P to Q along C1 plus from Q to P along C2 in opposite direction. Therefore this integral sum is 0. Now first part is P to Q, that is integral over C1, and second one is from Q to P, means it is minus of C2, opposite direction. C2 is the path from P to Q, along C2 from Q to P is nothing but minus C2, and hence integral over C1 f of z dz minus integral of f of z dz along C2, that is equal to 0. Therefore integral of f of z dz along C1 is equal to integral of f of z dz along C2. That means C1 is nothing but the path joining P and Q from P to Q. C2 is also another path. Therefore integral of f of z dz from P to Q is independent of this path. So in any path the integral is same. One more corollary. If C1 and C2 are 2 simple closed curves such that C2 is entirely within C1. Now this is the curve C1 and C2 is inside C1. 2 closed curves. Now the closed curves you are going to consider in anti-clockwise direction. C1 means like this, anti-clockwise. C2 is also in anti-clockwise direction. If you consider it in clockwise direction, then it is minus C2. Okay. Here the concept is, if f of z is analytic on C1 and C2 and in the region bounded by C1 and C2, that means along the curve C1 and C2 and between C1 and C2. So in this region f of z is analytic. Then integral over C1 f of z dz is nothing but integral over C2 f of z dz. So no need to integrate along C1. It is enough to integrate along C2 because it is analytic between C1 and C2. That is the concept. How we can prove this? And this region is called annular regions. This region between C1 and C2, this is annular region. Okay. Now to prove this, assume that AB is the cross cut in the region between C1 and C2. That means you are going to take one cut here at the point A and B. A is on C1 and B is on C2 and cut this region. Now region looks like this. Just separate this. That means A and B, that point. So you cut the region A and B. Now consider the closed curve. How to consider that? C is the curve from A to A along C1 So this is anti-clockwise, therefore I am going to consider it as positive. And from A to B, and then from B to B along C2 in clockwise direction, and then from B to A. So totally it becomes closed curve. Now in this closed curve C, f of z is analytic. Within and on the closed curve C, f of z is analytic. And hence integral of f of z dz along this curve, closed curve, is 0 by Cauchy's theorem. Now the closed curve C is nothing but from A to A along C1 in anti-clockwise direction, and from A to B, and then from B to B along C2 in clockwise direction, and then from B to A. Therefore it becomes totally, C becomes closed curve from A to A. And hence by Cauchy's theorem, integral over C f of z dz is 0. Now C is split into 4 parts. One is A to A along C1, and from A to B, and then from B to B along C2 in clockwise direction, that is minus of C2, and then from B to A. Therefore left hand side is here integral of f of z dz along C1 and from A to B f of z dz and along C2 in clockwise direction, therefore minus of integral f of z dz along C2 and from B to A f of z dz. So this becomes 0. And we know that integral from A to B is nothing but minus of B to A integral, and hence these two cancels. The remaining term is integral over C1 f of z dz minus integral over C2 f of z dz equal to 0, and hence integral over C1 f of z dz is equal to integral over C2 f of z dz. I hope you got the idea. That means if the closed curve C2 is within C1, then and between C1 and C2, if the f of z is analytic and it is analytic on the curves also, then integral over C1 is nothing but integral over C2. Next one. Okay, one example. Verify Kaushis theorem on integral e power iz dz along the curve C, where C is the boundary of the triangle with the vertices at the point 1 plus I, minus 1 plus I, and minus 1 minus I. Now 1 plus I, let it be P, minus 1 plus I is Q, and minus 1 minus I is R. Therefore P is the point in x coordinate is 1, y coordinate is 1, and Q is the point x coordinate is minus 1, y coordinate is 1, and R is minus 1 minus 1. Therefore boundary of the triangle means it is from P to Q and from Q to R and from R to P. So this is totally, it becomes C, the curve C. Now since it is closed curve, integral over C e power iz dz is nothing but integral over C1 plus integral over C2 plus integral over C3. Now C1 is nothing but P to Q. Here y is 1, equation of PQ is y equal to 1, and equation of QR is x equal to minus 1, x is constant here, and equation of PR or RP, that is x equal to y, and hence along PQ y is 1 and dy is 0, no change in y, y remains same here, y is 1, and along QR x is same, that is minus 1, and hence dx is 0, no change in x, so dx is 0, and along RP x equal to y, therefore dy is dx, y equal to x, and hence dy equal to dx along RP. Therefore integral over C e power iz dz is nothing but integral from P to Q plus integral from Q to R plus integral from R to P. Now z is x plus iy, dz is dx plus I dy. Carefully substitute. P to Q means x vary from 1 to minus 1, x from 1 to minus 1, P to Q, x vary from 1 to minus 1, e power I into z is x plus I y, but y is 1, substitute y is 1, therefore e power I into x plus I, and dy is 0, therefore dz becomes dx plus I dy, dy 0 means it becomes dx, and then q to r means here x is minus 1, y varies from 1 to minus 1, y varies from 1 to minus 1, e power I into x plus iy, x is minus 1, and dx is 0, therefore dx plus I dy becomes I dy, put dx is 0 in dz. Okay. From r to p means x varies from minus 1 to 1, x from minus 1 to 1, and y equal to x, therefore z is nothing but x plus I y, y is x means x plus I x, take x outside, so 1 plus I, so e power I x into 1 plus I, and dz is dx plus I dy, but dy is dx, take dx outside, 1 plus I into dx. Now carefully integrate. You know that integration of e power ax plus b is nothing but e power ax plus b divided by a. Therefore, integral of e power I into x plus I is nothing but integral of I into x plus I divided by coefficient of x, that is I. E power I into x plus I divided by I. Limit of x is from 1 to minus 1, upper limit minus 1. And next one is e power I into minus 1 plus iy. You are integrating with respect to y. This I is taken outside. I into e power I into minus 1 plus iy divided by minus 1. Because here coefficient of y is I into I. I square is minus 1. So divided by minus 1. Careful here. Coefficient of y is I into I. Here is outside one, I is there. So I square is minus 1. And limit is from 1 to minus 1. And last one is e power I into, here 1 plus I constant, take outside, e power I into x into 1 plus I divided by coefficient of x is I into 1 plus I into 1 plus I. Limit is from minus 1 to 1. Okay. Now carefully apply these limits. Upper limit is minus 1 here. X is minus 1. Therefore, e power I into minus 1 plus I divided by I. So 1 by I is minus I. This is upper limit. And lower limit is 1. So upper limit minus lower limit. Lower limit value is e power I into 1 plus I divided by I, that is 1 by I is minus I, therefore lower limit minus, so it becomes plus I into e power I into 1 plus I. Here upper limit of y is minus 1, therefore it is minus, this minus I into e power I into minus 1 plus minus I. Take minus outside, 1 plus I. Minus 1 minus I is nothing but minus of 1 plus I. Minus lower limit is 1, but here is on minus, therefore it becomes plus I into e power I into minus 1 plus I. Minus 1 plus I. And last one is here 1 plus I is cancelled. Cancel 1 plus I. 1 by I is minus I. Upper limit value is 1. Therefore, minus I into e power I into x value 1. 1 into 1 plus I minus lower limit value is minus 1. Therefore, minus of minus plus I into e power minus I into 1 plus I. Now, observe this carefully. The first one and here fourth one same with minus sign. This is minus, here plus sign cancels. and second one and fifth one same with the opposite sign cancels, and third one and sixth one same with the opposite sign, so it cancels. Therefore, that becomes 0. So this is equation 1. But f of z is e power I z is analytic everywhere, and hence in the closed curve C is also analytic. By Kaushis theorem it is 0. Now from 1 and 2, here from 1 also we got integral over C e power I z dz. By line integral method we got 0, and by Cauchy's theorem direct one, so it is 0, and hence Cauchy's theorem is verified. I hope you got the idea how we can verify the Cauchy's theorem. So this is by theorem, integral value 0. This is by line integral method, so integral value is 0. Okay. Next one is Cauchy's integral formula. Statement is, if f of z is analytic inside and on a simple closed curve C, that means within and on the closed curve C, and if A is any point within C, A is any point within C, then f of A is equal to 1 by 2 pi I into integral over C f of z by z minus A dz. Now, how we can prove this theorem? The concept here is, A is a point within C. We shall enclose it by a circle C1 with center at A and radius R, here fixed R, and select R such that the circle C1 lies entirely within C. So select one circle C1 with radius R and center at A. Select R such that that circle is entirely within C. Now, see this is your circle, curve, closed curve C. Now take any point within C, A is any point within C, inside C. Consider a circle of radius R. The C1, circle C1 is entirely inside the closed curve C. Now the function f of z by z minus A. Now you are going to consider this function. Actually it is not analytic at z equal to A, because denominator becomes 0 means it is not defined. Therefore, f of z by z minus A is not analytic at z equal to A. But at every point, other points it is analytic, because f of z is analytic, and hence f of z by z minus A is also analytic. Hence between C1 and C, or C and C1, the function is analytic, and along the curve C1 also it is analytic, and along the curve C is also it is analytic. And hence here the equation of this circle C1, parametric equation of the circle C1 is, take any point on the z is any point on the circle, and from A to Z the distance is R. R means fixed constant, it is not variable, so parametric equation it is. Now Z minus A is R e power I theta, and Z is nothing but A plus R e power I theta. Theta varies from 0 to 2 pi, that is the circle. The equation of the circle C1 is Z minus A is R e power I theta, or Z equal to A plus R e power I theta, where theta varies from 0 to 2 pi. Differentiate Z with respect to theta. dz by d theta is A constant 0, R is also constant, e power I theta derivative is I e power I theta. Therefore, dz is I R e power I theta d theta. And by the corollary or consequence of Cauchy's theorem, integral over C f of z by z minus A dz is nothing but integral over C1. So integral over C is nothing but integral over C1, because f of z is analytic, f of z by z minus A is analytic between C and C1, and on the curve C1 as well as on the curve C, and hence integral over C is nothing but integral over C1. by the Cauchy's theorem consequence, integral over C f of z by z minus a dz is integral over C1 f of z by z minus a dz. C1 parametric equation of C1, that is theta varies from 0 to 2 pi and z is a plus r e power I theta, z minus a is r e power I theta and dz is I r e power I theta. Here you cancel r e power I theta and I you take outside, therefore it is I into theta varies from 0 to 2 pi f of a plus r e power I theta d theta. But here this is true for any circle C1 within C. So select C1, that circle C1 is defined by this R. R may be any small, then also this answer is same. Consider R such that that circle is almost a point circle. That means R tends to 0. When R tends to 0, then also this integral is same. And hence integral over C f of z by z minus a dz is I into integral theta from 0 to 2 pi f of a, because r is 0 means f of a d theta. Now f of a is constant, take outside, I into f of a, integral of 1 is theta, upper limit is 2 pi, lower limit is 0. Therefore it is 2 pi I f of a. So integral over C f of z by z minus a dz is 2 pi I f of a, and hence f of a is nothing but 1 by 2 pi I into integral over C f of z by z minus a dz. So that is the required result. F of a is 1 by 2 pi I integral over C f of z by z minus a dz. Now we can generalize this theorem. If f of z is analytic inside and on a simple closed curve C, and if a is any point within C, then f of nth derivative of a, that means nth derivative of f at x z equal to a is equal to n factorial by 2 pi I integral over C f of z by z minus a power n1 into dz. Now how we can prove? By the Cauchy's integral formula, we have f of a is 1 by 2 pi I integral over C f of z by z minus a dz. Now differentiate this with respect to a. Left hand side is f dash a, right hand side is derivative under integral sign, it becomes partial derivative. Therefore f of z by z minus a dz with respect to a partial derivative is nothing but f of z by z minus a whole square. See this 1 by z minus a derivative with respect to a is minus 1 by z minus a whole square into derivative of minus a is minus 1. Therefore plus 1 by z minus a whole square. So f dash a is 1 by 2 pi I into integral over C f of z by z minus a whole square dz. Now again differentiate with respect to a. So f double dash a is equal to 1 by 2 pi I integral over C f of z by z minus a whole square derivative, partial derivative is nothing but minus 2 into 1 by z minus a whole cube into minus 1. Therefore 2 by z minus a whole cube. Now 2 is nothing but 2 factorial. So f double dash a is 2 factorial by 2 pi I into integral over C f of z by z minus a whole cube dz. Similarly, this is second f double dash. Similarly, f triple dash a is nothing but one more 3 comes here, 2 into 3, that is 6, or 3 factorial by 2 pi I into integral over C f of z by z minus a power 4 dz. Z minus a power 4 dz means n plus 1, nth derivative, third derivative. Here 3 plus 1, 4. So in general you can write f nth derivative at a is nothing but n factorial by 2 pi I into integral over C f of z by z minus a power n plus 1 dz. So this is the generalized form of the Cauchy's integral formula. So with the help of these formulas, we are able to solve some integration using Cauchy's theorem and Cauchy's integral formula, that I am going to discuss in the next lecture, the last one in this module. I hope you got the idea of this Cauchy's theorem proof and Cauchy's integral formula derivation. and with the help of the consequence of Cauchy's theorem, we proved the Cauchy's integral formula concept. Thank you for watching.